Swayam Prabha. Digital India. Educated India.
So let's restate this problem, and this problem is what is called multidimensional scaling. I think there's somebody in our set of participants who had a background in statistics, right? Is the participant still here? Right? So this particular topic is commonly studied in statistics. It's called multidimensional scaling. The problem is this. So let's say we are given n points in some RK. We are given pairwise distances. Okay. We are not given these points to begin with. Okay. So that, I mean, when I say that there are x1 to xn in RK, we are not given these points. Okay? We are only given distances between them. The question is, can we find what these points were given the pairwise distances? So this particular problem is what is called MDS, and we'll see how attacking this problem helps solving the above problem. Right? How does it help? So instead of taking these as straight line distances, all I have to do is to use the geodesic distance between xi and xj. Okay, so I'm going to use this as the data. Traditionally, in multidimensional scaling, what is given is the straight line distances are given. From straight line distances, we have to find what are the set of points, right? In our case, what we'll do is, instead of assuming this as the straight line distance, we'll assume that this is the geodesic distance. Okay, that's all. Right? And the idea would be to obtain these set of points such that the straight line distance between xi and xj in Rm, right, is equal to this geodesic distance. That's how this problem is related. Okay, how this is related to statistics, or in fact even psychology. So the problem goes like this. So let's say you have n candidates and you interview them. From these interviews, you find out how dissimilar each candidate is to each other. Okay, and now you want a graphical representation of these dissimilarities, right? How would you do it? So you will try to find points. Each point represents a particular candidate, such that the distance between 2 points is equal to the dissimilarity that you have figured out between those two candidates. Okay, that is sort of a very basis of this multidimensional scaling. You want to have a graphical representation of dissimilarities. That's the key. So again, the idea is these distances can be thought of as dissimilarities, and you don't care whether those dissimilarities come from straight line distances or any other way. Okay? You assume that this is your given data. From that, you want to construct a set of points whose distances are given by these dissimilarities. So that's the history behind this. Let's try to see how to solve it. So now I won't be able to avoid equations anymore, even if I like. So here they are. Straight line distances, right, between xi and xj. The squared straight line distance can be written in this way. Agreed? This should be familiar to all. Okay, I'm just opening out this square, that's all. Then, so let us capture the squared distances in an n by n matrix called D. Okay, let us write the norm squared of these individual vectors. And once again, I know we are not given x1 to xn, right? But I'm just trying to move towards a method that tries to give us x1 to xn. So there's some math here that I'm going to do. More than math, it's just manipulation of data here and there. So let A denote this n by 1 vector whose entries are nothing but squared norms. Okay, and let X denote basically the set of points that I want to compute. For now, I am assuming that these x1 to xn, so the points that I want to represent are in R3. Okay, so each point is a three-dimensional vector, x, y, and z coordinates. And because again, remember, typically this is useful whenever you want to display this information. Okay, since you want to display it, it doesn't make sense to use a k greater than 3. Okay, so we'll restrict ourselves to k equals 3. We can go below 3, of course, but for now we'll restrict ourselves to the case where k is equal to 3. With this notation, this distance matrix can basically be written in this way. Can you see why? So the ijth entry of this would be what? The right hand side first is a into 1. So what happens if I multiply it by a row vector of all ones? So A1, A2, A3 into vector 1, 1, 1 is this matrix, right? A1, 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 A2, 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 and A3, A3, A3. Right? So what would be the ijth entry of this matrix? Would be norm xi squared. What would be the ijth entry of 1a transpose? 1a transpose is nothing but the transpose of this. So it would be xj squared. And what would be the ijth entry of xx transpose? Xx transpose, remember, is again an n by n matrix. What would be the entry? Would just be minus twice I transpose xg. Okay, and that is basically this equation. All right. Okay. So then taking xx transpose on the left hand side, shifting everything else gives you this. How does this help? So D is given. If I had known what was A, right, then I, in some sense, could have computed X or XX transpose directly, and from XX transpose, it's basically a factorization problem, right? I want to factorize this thing into two matrices, one I call X, the other X transpose. So that has well-known solutions. But unfortunately, you look at the right hand side, A itself depends on these unknowns, Xi's. All right. How do I find that? The thing is, we cannot find A. Surely we cannot do anything about it, right? What are these? These are distances, right? Between these points. That is our assumption. Now, does it matter whether the points are X or whether the points are X shifted by some translation vector? Is the distance going to change if I change X to X plus some translation vector? No, right? This is something we have been discussing almost throughout the summer school, that the distance between points is invariant to any rigid transformation. Therefore, it is invariant to translation also. So let's translate the points x. Question is where? So what is this matrix? 1 by n into 1 transpose x. Quick answer. We're running out of time. It's okay. What is 1 transpose x going to give you? 1 transpose is this vector 1. X is this matrix x1 transpose xn transpose. This is 1 by n by 3. Sum of all xi's, right? And then there is 1 by n. So what is this? So overall in average, what is this average? It's also going to be a 1 by 3 vector, right? What is this point called? Remember Swayash's session? Is the centroid. Okay. What happens if I multiply this vector 1 to this centroid vector? So you can think of 1 by n 1 transpose x also as 1 by n 1 transpose x. What will this do? So if I denote the centroid vector by c, which is a 1 by 3 vector, what is 1 times c going to give you? It's just the centroid copied over n rows, right? Okay. Then this question is what is x minus this vector? Again, I hope you see this is something you have done in the second session. Translation distance, something more specific. What would be the centroid of this new set of endpoints? Origin, right? So this is this origin centered x. Right? And another way to write this is just the identity n dimensional identity matrix times 1 transpose x. Okay. And this matrix is going to play a very important role in MDS, multidimensional scaling. We'll denote it by the alphabet J. Okay. So the question is, if X satisfies the pairwise distance matrix D, would Jx also satisfy the same distance matrix? Anyone else? So the only difference between X and Jx is a translation. Of course, a very specific translation, but as far as the answer to this question is concerned, the only notable thing is that they are translated. And we've seen translation doesn't affect the distance. So if x satisfies the distance criteria, gx will also satisfy the distance criteria. So instead of looking for any general x, we will look for an x whose centroid coincides with the origin. In other words, we look for points of the kind or the matrices of the kind jx. Okay, so let's substitute this jx back in this equation here. Okay, fine. So pre-multiplying by X and post-multiplying by J transpose. By the way, what is J transpose going to be? You can see from here. What kind of a matrix is J? It's a symmetric matrix, right? So whether you write it J transpose or J, it doesn't really matter. Okay, so let's just see what happens if I pre-multiply by J and post-multiply it by J or J transpose on both sides. You get this thing. 1 transpose J transpose. What is that going to be? You can clearly see 1 transpose into identity is 1 transpose minus 1 by n. 1 transpose into n. 1 transpose is this row vector, 1 is this with all ones. So this will add up to n into n into 1 transpose. This n cancels, 1 transpose minus 1 transpose is 0. Okay, so this is 0. Similarly, you can show that j times the vector 1 is also 0. What that gives us is a disappears completely. Okay, and finally you are left with, so instead of, so I'm just introducing a new notation for jx. Instead of jx, I will use y. Y transpose must be equal to minus half GDJ. J is a matrix that we can construct. D is given to us. All we have to do is, if I call this matrix B, then B is available. From B, I need to factorize this two matrices, Y transpose. And Y is nothing but your origin centered X that you are looking for. All right. So far, so good. Any problems here? Any issues still now? Nice to get some feedback. Sharing no doubts. Have I put all of you to sleep? Okay, so now how do we solve this problem? The matrix B is given, I want to decompose it into Y and Y transpose. Of course, what are the dimensions? Y is n cross 3, Y transpose is 3 cross n. Okay, that's a problem in linear algebra, and well-known solutions exist. So this is the problem, right? Either I write it in this way, that you find a y which satisfies this equation, or I can take this on the left hand side and say that I want to find a y such that y transpose minus b is 0, or if not 0, at least bring it as close as possible to 0. Right? So this y transpose minus b will be a matrix. I want all its entries to be as close as possible to 0. That is what this denotes. Right? So, are you familiar with this notation, everybody? This F, it stands for Frobenius norm. Anybody who is not familiar with this? Do you want me to explain what this Frobenius norm is? No replies. Are you all hungry so early? Are you all familiar with Frobenius norms? Should I assume that, or do you want me to explain it? Tell me something. Okay, I mean, no responses. I will assume you are familiar. I don't know. But please, in case you are not, still let me know. We can, it's not very complicated. Right, Vignesh, I understand that, but I'm asking individually, are all of you familiar? Vignesh is, I'm sure. Darshil should be, I think. Anybody else? Sarah is good. Sanchi, are you familiar? I hope you are. Not, please let me know. Omkar is familiar. Good. Tushar is okay. Fine. Okay, now how do you solve this? Do any one of you know how to solve this problem? What is the key here? Y has to be a n cross 3 matrix. Right? And what sort of a matrix is B? What happens if I take a transpose of matrix B? B transpose is equal to J transpose, D transpose, J transpose, J, D. Both of them are symmetric matrices. So therefore B transpose is B. So SVD, have you heard of SVD? Everyone? Singular vector decomposition. Okay, so I hope all of you know what this is. If B, I mean, for any rectangular matrix A of size m cross n, you can write it as a product of three matrices U, which will be typically of size m cross m, a diagonal matrix sigma of size m cross n, and V star of which is conjugate transpose or V transpose. This would be of size n cross n. Special thing about this decomposition, apart from this central matrix being diagonal, is that U and V, both of them would be orthogonal matrices, M and N. Okay, and since B is a symmetric matrix, square symmetric matrix, of course, so U and V will be the same, which is why it is guaranteed that you can write B as U sigma U transpose. So it's basically an eigen decomposition as well. Okay, so once that is there, then you can pre-multiply and post-multiply by U transpose and U respectively to this cost that you're trying to minimize. Remember, Frobenius norm is invariant to multiplication by any orthogonal matrix. Therefore, you get this expression. This is just a diagonal term, right? Sigma. So how do you find a Y which minimizes this? Okay, remember this is diagonal, right? So all non-diagonal entries are zero. So if you want to minimize this cost function, you should also ensure that this matrix also has non-diagonal term zero, right? So of course, a choice would for y could be u. Because if I put y equals u, I get u transpose u, which is identity, u transpose u, which is identity. Okay, so of course, this becomes something like an identity matrix. But of course, remember, y has to be of size n cross 3 only, whereas u will be of size n cross n. So what I can do is I can pick, I'm going to go with Python notation. So I can pick the first 3 columns of u. Right? That is going to ensure that I get basically an identity matrix. But unfortunately, this sigma is not an identity diagonal matrix, right? It has certain values, sigma 1, sigma 2, and so on and so forth. So you have to multiply this with a diagonal matrix with the same values. That's going to be your y. That minimizes this cost function. And square root, because there is a not only y, there is y transpose. You square root the sigma values, y transpose will ensure you get sigma values. So that is your solution. Okay, so this is again something that you are going to code in the afternoon session, right? And you can see basically what you have to do is take make the matrix J. Once you have the matrix J, D you can assume is given to you. It will be given to you. Form this matrix P and just compute its SVD. Select the first three columns of U and the first three singular values and make this Y. That's going to be your solution. And I hope you're following this discussion. Will not very complicated. Okay, and that brings us to the final algorithm. And so we look at this algorithm. What it does is it tries to minimize this. Right? It does not directly try to minimize the distances between the points y that you have obtained and the distances which are originally given in the distance matrix D. There is no direct optimization that compares these two distances, straight line distances of points in Y with distances of the corresponding points given in the matrix D. There is no explicit comparison that's happening over here. So a more direct approach to this is what is called a minimum distortion mapping. Idea is again simple. So let's say X be a point cloud and you are given pairwise geodesic distances in this matrix Dx. Okay, you want to find points Zi's I going from 1 to n such that what should happen? The straight line distance between Zi and Zj must be as close as possible to the distance between the ith and jth vertex given to you. Okay, so ijth entry of this matrix Dx. And you would want, of course, both of these are symmetric, right? It doesn't matter whether it is Zi Zj or Zj Zi. Similarly, Dx Ji and Ij is the same. So we can sum this up over all i's greater than j. Make sense? Okay, so this expression on the right hand side is sometimes also called stress, or I think more specifically this is Kruskal's stress function. And again, straightforward optimization problem to find minima z star that minimizes the 2 stress. The 2 in the sense because again this is squared, right? The error between the given geodesic distance and the realized straight line distance is squared. So it's sum of squared, which is why this is called the 2 stress also, or sigma 2. Right. So I'm going to skip some math because there's not much time and I don't want to harass you guys. I can expand this. So this is pretty straightforward. So dxij squared dmzi squared minus 2 dxi dmzi zj. Okay, that should be straightforward. I'm going to write at least these two parts using matrices directly. Okay. How to write them as matrices is given in my slides. I've already uploaded the slides on the Google Drive. Just because there's not enough time, I'm not going to go through all this derivation, but I've sort of tried to give all the details as far as possible, so you can go through this. This term dmzi squared can be written as this trace of Z transpose. Remember, Z is n by 3. This matrix B is a very simple matrix, right? All off diagonal entries are -1 and all diagonal entries are n-1. Okay? So it's a constant simple matrix V of size n cross n. Z is n cross 3. So that is how you can write this. Okay, the derivation, let's not bother about it. Similarly, I think I have this. Yeah, yes. So this last term, right? Summation over all ij's, dxij, dmzizj can also be written similarly as a trace of X transpose times a matrix B. This matrix B itself is a function of Z dx, okay, times the matrix X. And this matrix is defined this way. It looks complicated, but it's very closely related to the matrix B. Okay, so for now, just assume this is the case. The derivation, I didn't even think I will do it in the class. So, but still, I've given the proof for those who are interested in manipulating numbers and into matrices. There's nothing else here. So let's just forget that for now. Right. So that gives us the two stress as this matrix or trace of this product of three matrices to this plus this term. Now remember, this is it's not at all a function of your optimization variable z, so you can basically ignore it. Why we did this is because now it's very easy to solve this, right? Because all we have to do is, it's a least squared function, so it is differentiable, it is convex. So you can just differentiate. Sorry, I don't. So I'm sorry. I take back that. It's not a convex function, but at least it's a squared function. You can differentiate this with respect to z. Differentiating these terms with respect to z becomes very easy. It's just twice. So it's just like a quadratic function, vz square. That would be 2vz, and this would again be 2vz squared. So this would be twice. Sorry, this is just like a linear function. I think I made a mistake here. No, this is okay. So 2bz into z, and it's also a quadratic in z. And then what we do is just a gradient descent. Okay, so this is the gradient. You start with some estimate z of z, it's zk. Take a time step along the negative of this gradient. This is why you get this, and you keep on iterating till you reach a point of minimum. Okay, so that's how this looks. Uh, Still just 10 minutes left, and there is something that will take more than 10 minutes, and I don't want to torture you. But slides are there. This can be seen as a very special optimization technique, which is what is called optimization by majorization. Since I did the optimization part, I thought let me also sort of give the optimization details, but we don't have enough time. So I'm just going to leave the slides as it is, and those of you who are interested, you can let me know. I will explain this sometime later. I don't, again, I do want some of you to return in the afternoon session, and just for that particular reason, I'm not going to harass you. So let's leave all of this. I'm just directly going to go to the references. Okay, so if you're interested in following more details of whatever I have explained, you can look up these particular references. This I have already given in the earlier slides. This is sort of the classical paper that talks about the ICP algorithm. This paper again is the one that talks about modifying the cost function so as to uh, have a scheme which is insensitive to outliers. For the non-rigid shape matching part, basically used something called MDS, multidimensional scaling. There's a book on this, even over here. I think it is available on LinkedIn. So you don't have access to this through your library. It is available. And this particular algorithm that I didn't talk about, the Smakoff algorithm, was first given in 1977 by somebody called John de Leeuw. Forgot to write the name of the author here. So here's the name of the author. Okay, take a look at this paper as well. And of course, there are more recent variants of this particular algorithm that looks at the Laplace-Beltrami operator and its eigenfunctions. I wanted to do that, but again, we just don't have time. Okay, the idea is very simple. Now, if you look at this SVD-based algorithm that we gave, what do we need in this? There's two things we need, right? The matrix J and the matrix D. What is a matrix D? So let's say you have a mesh which has 50,000 vertices. What would be D? I hope some of you are still here. Uh, what is this matrix D going to have? Anyone?
50,000 cross 50,000 matrix.
And its entries would be
A distance between 2 points.
what sort of a distance?
Geodesic distance.
Geodesic distance. Now,
Yeah.
just think about it. To get that matrix D itself is going to be computationally very, very expensive, right? Apart from memory issues. Okay, so what is done more recently is, so think of that distance matrix as an image, right? Now, if I give you some sample points of the image, can you try to reconstruct the entire original image? Right? Yes, right. I mean, for example, what you can do is what is done in JPEG, right? You work in the Fourier transform domain. In the Fourier domain, you only need a few coefficients in order to store or preserve most of the image. Similarly here, yes, exactly, compressed image is reconstructed. So I can sort of save only, let's say, first 10 DCT coefficients, and from that I can reconstruct the entire image. Of course, there will be errors, but as far as the image is smooth, the errors will be lower, right? Those of you who have been exposed to image processing, they should realize if there are fewer edges or discontinuities, then smaller number of coefficients will be able to do a better reconstruction. So similarly here, D, this distance, what sort of a function is it? Does it have too many discontinuities? So if I look at one row of this distance matrix, right, what does it? It's like distance of one particular vertex from all other vertices, right? Now, if I'm traversing on a mesh, right, is that distance function going to change drastically? No, right? It's like if I move to a neighboring point, the distance is only going to slightly change. In fact, I think if you have attended Professor Ojaswa's class, you would have seen this equation. Does anybody recollect the name of this equation? It's so-called iconal equation. What does this say? It says that the most that the distance function can change is 1. So which means that the distance function is a very smooth function. And so, given only few samples of this distance matrix, I should be able to reconstruct this large distance matrix using only a very few Fourier coefficients. By Fourier coefficients, I mean the Laplace-Beltrami operator eigenvectors. Okay, that particular way of doing MDS is aptly called, I'll just write it down for you to search on Google later on. It's called spectral MDS. Okay, so yeah, there are several other things that one could talk about. And apart from these methods, there are methods that do not try to find correspondences. They directly try to match the shapes using distributions of features that capture local shape properties. But for that, there should have been another session. So I think I'll stop here. Once again, I hope most of you are able to attend the afternoon sessions. So knowing the theory is one thing, but if you don't actually get your hands dirty, it may not really reinforce the concept. And what I've given to you is not something very complicated. I've already written parts of the code and made it available to you. You can go to my Google Drive folder and download this folder that I think I've called shape matching. So I don't think it's complicated. Please do show up at 2 o'clock. Okay, so with that, we are precisely at noon. We'll stop this session.